Monday. I don't think we were here Monday, Sunday, whatever. I am getting myself confused about the days of the week now. We left off on recursion, and I promised you I would get back to it, and I am valiantly, there we go. What we did was we came down and we started looking at the advanced examples. And I think this is important because if we don't look at the advanced examples, it's going to be hard for you. The final is cumulative. Sometimes on the little toy problems, it's hard to get the real feel for the usefulness or the structure of recursive algorithms. So we are going to start looking at some different types of algorithms. We looked at this briefly. Our next lecture, Lecture 22, which will start as soon as we're done with the recursion, is going to talk a little bit more about tkinter, which is the way we actually built this interface, built this project. So I'm not going to talk about that too much, but I do want to kind of walk through a little bit here. This is the tkinter example for okay, that looks like it's showing. tkinter example for the Sierpinski's triangle, which is an example of recursive figure, a fractal essentially. If we set the depth all the way to 0, and then we run, what we're going to see is the whole recursion is within this function draw triangles. And what draw triangles does is when it comes in, it's given an x and a y and a length and a depth. And the depth is how many levels of recursion is done already. That's just our limiting factor on how far down we want to go in our program. What we do is we actually draw a polygon. This is the formula to draw a polygon starting at point x and y. It's essentially it is a equilateral triangle. So we start at x and y. We go to x plus length, right? So that's along the bottom edge, and then we go up to the peak, which is x is at the midpoint and y is like the square root of 3 over 2 times the midpoint, or something like that. Square root of 3 over 2 times the side length. And we just draw a triangle and we fill it in red. And if we run our application right now, what we'll see is if we draw it, that's exactly what we draw. We're at depth 0. We come in, we draw a red triangle, and then we hit this if statement, and we are already at our depth is 0, and our maximum depth is 0, and we stop. So we bottom out the recursion. For this particular one, the recursion is based on how many levels of triangles you've actually drawn. Okay, so now let's look at what happens if we have depth equal to 1. Right, so if we have depth equal to 1, we start off, depth is 0, we come in and we draw the red triangle, and then we come in, depth is less than, we're at depth 0, our maximum depth is 1, so we want to come in here and, or I guess our...
Professor, your audio sounds very strange.
Huh. I am not doing anything different, and it's good on the capture side, which means that has to be a network problem. Is this something that everybody's having? If so, I can kill this and try again. I got...
I'm having it. I'm having it as well. I think everyone is.
Well, let's see what happens if I... leave the meeting and try to rejoin. Let's see if this will work. If this bombs out, just come back and start again. All right, I'm going to, I started again. We'll see if this works. I took back my hosting job from Kristen. Thank you, Kristen, for being my surrogate for a few minutes. All right, good. Okay, let's continue on then. So, yeah, depth is the number of recursive calls, and I may be off by 1 on whether we start off with depth equal to 1 or depth equals 0. Yeah, okay. So, anyway, if we haven't bottomed out our recursion, we come in and we draw a white triangle in the center of this red triangle, right? So this is what we're drawing there. This is an inverted white triangle inside. And then we proceed to do the draw triangle again on each of, right? If we draw a white triangle in the center here, that's going to create 3 red triangles. So we immediately go and recurse on each one of those upper triangles, or each one of the remaining red triangles. So let's see what happens when we get down to 1. If we increase our depth
Professor,
to 1,
it's
yep.
still a bit choppy.
Okay, I think, yeah, I'm not sure what I can do about that, unfortunately. I don't
Maybe try turning off your camera.
Okay, maybe that'll work. Okay, is this better? Okay.
Not much, no.
Yeah. What I am wondering about, let me see if we... Okay, is this any better? All right.
That sounded better, yeah.
Okay, so it sounds like we may have had somebody else stepping into the audio, which I should have checked to begin with. All right, so let's go on with this. So anyway, so we come in here. If we make this equal to 1 and we run it again, right? We draw the white triangle, then we recurse on each of the remaining 3 red triangles, right? Triangle 1, triangle 2, triangle 3. So this recursion has 3 parts to it. We recurse on those three statements, and these essentially define the upper, the leftmost, and the rightmost triangle. And as we increase that depth, what we'll do is we'll extend our recursion into each one of those triangles, etc. And it's really a fairly simple call to do all this, right? All the draw function does, we come in, we draw a polygon. If we're not done, we draw the white polygon, and then we recurse. And because of that, we're able to go down and we're able to create an arbitrarily, at least we max out at 9 for this particular one, but we can draw an arbitrarily sophisticated triangular figure. Okay, so that's just a little bit of visual recursion to essentially draw a fractal. There, I'll pull that back a little bit. That wasn't really all that visible at level 9. So now it's sped up a lot, and we can actually see the structure inside as we zoom into the different triangles. So, and this is what you're actually going to do with your lab in some sense. You're not going to be drawing triangles. You're just going to be drawing plus signs. So, that this structure though is what you're looking at. You'll be drawing 4 of these, right? You want to draw a new figure on the ends of each of the arms of your plus sign, upright, and the horizontal. And we'll get into these a little bit, but Canvas Update just says update it, make it look pretty. Draw everything that I've told you to do so far, and this just says wait a little bit of time so that we can actually visually see what's going on. So without that, what you'll end up getting is it'll draw it all before rendering it, and then you'll just get it blinking up onto the screen, or it'll draw it so fast that you can't actually see what's going on. So we can make this as fast as possible and draw again. All right. So anyway, that's what I wanted to talk to you about this one. That's one kind of visual recursion, and we'll talk a little bit more about setting up these buttons and how we set up this draw and everything in Lecture 22, which will follow Lecture 23 in a few minutes. Let's talk about two other ones that I want to kind of talk about. The first is if we have this idea of flattening a list. What if we want to take a list and we actually want to remove all sublists from it? And you may think, why would we want to do that? Well, if you look at this is actually a list representation of something you're going to learn about in data structures. It's essentially a list representation of a tree. If we go into, let's see if my camera still has batteries. Looks like it. If we go into this a little bit, essentially we have our V, and that was just me banging the camera. So in this, each list is a node, and then everything underneath that node is a child. So this V would have, if we just go through here, the first element in V is another list, which is 1, 5, and then 1, 5 has 2 elements, 1 and 5, right? So this is the first element of our list, and then we have a 6, and we have a list of 2, and then we have the actual 2, right? 2 is in a double list, and then we have another list, and then that list has a 3 and another list, and 7 and an 8 and another list, and a 9, another list, and a 9 and a 10, and then it had another list up here, which was 11 and 12. And normally with a tree, what we're doing is the tree is a structure for something, right? In this case, we have our tree being, our list being a structure for something. The tree is a structure for something, and all the interesting or informational data is actually stored down in the leaves, or at the bottom of the tree where we had all the numbers. So flattening the tree means going down and seeing what information you actually have stored, and the tree is storing the relationship between that information. So it's a very important operation, and it turns out that it's kind of hard to do without recursion. Yes, you don't need to know the graph stuff for the course, but it is an interesting, this is why it's an important, right, this is why this is actually something, flattening a list sounds kind of bogus. It's not a bogus problem, it's something we actually need to do. So when you're looking at this, the question you come up with is, well, how do we actually want to flatten this? So let's talk about this just a little bit. When we had the fractal figure, what we did was we decided that our recursion was going to be based on, our base case was going to be based on just how many levels we've generated. And we're going to use that to figure out how far we wanted to go. For this one, I'm going to start off with flat 1, and it's going to take a list V. And for this one, we're going to use a different base case, right? And we got to decide what that base case is. And I'm going to tell you that there's two different choices. There's at least two different choices that we can use on this. The first is we can recurse until we get a list that is all of simple arguments. So, you know, in this big list, we would look at this first element and we would recurse until we could print out, we could return all of this with no issue, right? So this is a simple list. We could return 1, 5. That would give us 1, 5, 6. Then we could do the same thing here and recurse on the list until all of the elements of the list are simple. Or we can recurse down until we've removed all of the brackets and assume that when we've removed all of the brackets, then we're down to so we can recurse down until we get to like the 1, for example. And both of these are valid. They do have some different behaviors in some of the degenerate cases. But let's start off. We'll choose. We're going to assume that at some level V is coming in as a list, and we're going to end our recursion when V is no longer a list. So if, and remember we've been using this type thing before. So if type of V is not equal to a list, right? So we're going to go through, and if we don't have a list, then what we're going to do is we're going to return a list with just V in it. Okay, so that'll say when we recurse all the way down to this 1, well, then that's going to be our terminal case, and we know that 1 is going to be in our final list, so we will return just that 1. So what if that's not the case? Well, if that's not the case, then V has to be a list, right? So now we can say for element in V, right? So we're going to take each element out of V one at a time. We'll start by taking out this 1, 5. And we'll say start, or I guess L. We start off with a blank list. For element in V, what we want to return is we want to create, right, as we go through and parse elements, what's going to be returned to us are simple lists. You know, lists with all the sublists removed. That's the whole purpose of the flattened one. So what we'll say is L plus equals, we'll do a concatenation between L and flat 1 of L. Of element. Okay, so what is this saying? Well, if we are a simple node, if we're a simple structure, we're not a list, then we know that the list we have to return just contains us. So we'll return that. If that's not the case, then we have something like 1, 5, and we can go through every element in 1, 5 and flatten that. So we'll go through every element, right? The first thing, the element will be 1, 5. We'll say, well, whatever we have, our empty set, we're going to append onto that or add onto that the results of flattening 1, 5. And then the results of flattening just the single value 6, then the results of flattening the list of 2, and so on. And then when we're done, well, then I think all we have to do is return L. Okay, so this is, I think, our entire recursive algorithm. And it's essentially just a tree traversal. You go down until you reach essentially the leaf of a tree, and then you put that leaf into the list. And if we run this, I got to kill my, there we go. Now we can run this, I hope. And we should have V is our list, And now we can do a flat 1 of V. And, right, we've pulled out first time through. We find this, we flatten that, we end up with 1, 5. Then we flatten the 6. We add the list whose element is 6 onto our 1, 5 list. Then we flatten 2, we add that in, and so on. So that's the first recursive version. It stops when we get down to, well, a simple element, something that's not a list. The issue with this one, and we could take care of this by doing some checks ahead of time. The issue with this one is it works fine with, if we give it an empty list, right? You flatten an empty list, you get an empty list. If you give it something like 3, which is not a list at all, it'll flatten 3, right? So you've turned something that's not a list into a list. And that may or may not be the behavior you want. We could get rid of that with some additional checks before we call the recursive part. But that is something to keep in mind. I said there were at least 2 ways. There are at least 2 ways. The other way you can do it is you can say, we'll do flat 2. I don't want to take too long on this one, but this one, what we'll do is we'll go through until, you know, every simple list we find, every list that only consists of single values, we will take that as the end. So instead of recursing down on this 6, we'll just add this 6 right in. So that's a little bit different. For this one, what we'll do is we'll just walk through the list for element in V. Probably still need a empty list to begin with. For element in V, if that's a list, we'll recurse. But if it's not, if it's a simple element, well, that will just depend on. And then at the end, of course, we have to still return L. I think that's right. So what does this do? Well, when we come through, the first time through, LM will be this list here. It is a list, so we'll go down and we will flatten it. When we flatten this, every element will be standalone, so every element will be appended onto L, and then that 1, 5 list will be returned up to flat 2. When we hit the 6, we will append the 6 right on to the end of the 1, 5 list we've already built. 2 is a list of a list, so it will be recursed on. It'll be recursed on again at the second level, etc. So I think this is going to work. We did flat 1. Let's do flat 2 of V. No, that didn't work at all, did it? Oh, geez. Doesn't work if you don't have the else clause. All right, let's try that again. There we go. All right. Yeah, we were appending both the list and the flattened list. All right, so you only go down, you only append if it's if you didn't have to flatten it. Either flatten either append the flattened one, or you append something you didn't have to further flatten. All right, this will behave the same on an empty list, I hope, unless I made a mistake. But when we get to something like 3, right, this is going to actually throw an error because we're iterating on our initial v. So, it kind of depends what behavior you want on your objects, on your lists, which one of these you actually want to use. All right, any questions about that? All right, so I think the last one we want to do is our merge sort. And I love this one because this is way easier than the way we learned merge to begin with. Oh, there we go. The merge algorithm is exactly the same. Okay, so we start out with our merge algorithm. All merge does, just to remind you, is that merge goes through and it takes two sorted lists and merges them into a bigger list that is still sorted. Okay, so if we want to do our merge sort, and we want to do that on a list V or a list L, let's do it on a list L, I guess. Well, so we have to define our base cases. Well, we know that that if we have a list of length 1, right? If we have a single element, we know that it's sorted. So a list of length 1 has to be sorted because, or 0, has to be sorted because there are no other opportunities, no other possibilities. So we'll make that our base case. We'll say if length of L less than or equal to 1, just to be safe, well, then all we're going to return is we're going to return L because L is already sorted. Okay, if that's not the case, then we have to figure out what to do. Well, we know that if we get to the point where we have just a single element, we're going to be good. So we can start thinking about, let's calculate a midpoint. And that's going to be the length of L divided by 2. We'll do it using integer divide. Right? And now that is going to divide our list into 2 equally sized lists. And we know that if we sort each of those equally sized lists, or approximately equally sized lists, if we can get those sorted, then we know we can pull them back together again using the merge to get a full size list. And that would be exactly what we want. So how would we go about doing that? Well, we know we have a sort routine. So let's say L1 equals merge sort from 0 up into mid, right? If we have let's walk through this a little bit. Right? So S is, length of S is 16. Length of S, integer divided by 2, is 8. And if we then take and look at S up through the mid, we have 1, 2, 3, 4, 5, 6, 7, 8 values. So if we sort, let me give us some space here. If we sort the first half of our list and we sort the second half of our list, right? And let's look at what mid colon is. right? That's the last 8. If we sort both of those, well then the sorted list is just L1, L2, right? We just merge those together, and that ought to work for us. Unless I typed in something wrong or forgot something. But, right, so this is what we're doing. We're saying, okay, we have a really hard problem. We got to sort this list. We know when we're done. We're done if we get down to a list of size 1. We know we're sorted. So let's figure out an easier problem that gets us moving in the direction of this 1. Well, the easier problem is to sort half the list, right? That's half as hard as sorting the entire list. So we'll do it twice. We'll sort the upper half and the lower half, and then we have this cool merge routine already available to us that allows us to just merge 2 sorted lists together. So we can run that to define those, come down here, and where are we defining L? I guess we're not. Do I have any? Okay. Let's do S equals list range 1000 import random Okay, so we have a shuffled S. S is not in any kind of order. And we can call our merge sort on S. And with any luck, T is going to be in sorted order. Okay? And if we look at this, right, this is exactly the same thing that we were doing in our non-recursive solution, but it's really much cleaner, right? This is why recursion is such a beautiful thing sometimes. And if we want to do an order bounds notation, well, we know that we're going to have to merge at the base level. We're going to have everything essentially lists of length 1. So we're going to have to go through and we're going to have to merge those lists of length 1 into, we're going to have to touch each one of those elements. And at the end, we're going to have 500 lists of length 2. So that's 1,000 operations, order of 1,000 operations. At the level 2, we're going to take all of those size 2 lists and we're going to merge them together, and we're going to end up with 250 lists of size 4, 125 lists of size 8. We could have made this 1024 and it would work out perfectly. About 63 lists of size 16, about 126 lists of size 32, and so on, right? So we know that each step through, we're going to have to touch each of the elements one time. So this merge pass is always going to take us order of n. So how many passes is it going to take? Well, every time we simplify our problem by a power of 2, right? So every time through the list, we have the size of our problem. So that's going to be, it's going to generate log base 2 levels, and the running time is going to be the number of times we have to call the merge routine, which is going to be log n, times the time of the merge routine, which is going to be n. So it's going to be, again, the recursion is going to be order of n log n, just like our original project, just like our original iterative solution. All right. Any questions about that? I know that's a lot of stuff. Take a look at it. This is one of my favorite ones. I learned the merge sort, the recursive merge sort, before I learned the iterative merge sort. It took me 3 or 4 semesters before I could do the iterative merge sort without making a mistake. This one I could do pretty much off the bat. But look, it's only like 8 lines, and that includes a blank, or the definition. All right, let me check the notes. All right, so let's go on to the next part of our exercise. Maybe before I do that, I want to put up my next section.